This video will demonstrate an automated design feature within Path Designer. I've loaded a large example. It's only 100 sites, which is not very much, but there's 4,915 50 rather paths loaded into this network in Path Designer. And what I'm going to demonstrate to you is that the tool will find the shortest minimal network design, a linear system, the shortest way to connect all of these 100 sites together from 4,950 possible paths, totaling 163,000 miles. And it finds the shortest route network way to connect them, which ends up being 131 paths, total of 399 miles. So it's essentially finding an optimal network in terms of shortest distance. Um, in the current development of this feature, there's no imposed constraints, but there are plans for constraints in future development, such as the slide says, number of directions on a structure type. For example, we don't want high voltage towers to be anything but an end of a link. We don't want to have it as an important hub. Maximum number of links between any site, or actually every site, and its POP, assuming that we would tag one of the sites as a POP or more than one, and the maximum number of sites connected to a POP. So any given route between a collection of sites to a POP site could be limited by the maximum number of sites carried or traffic carried ultimately. So those are future constraints planned, but I'll show you what we have today. So I'll just show you quickly the site manager here, which has 100 sites in it. They're just simple numbered sites, and they're actually been laid out in a simple grid just to show you a very congested but compact network as an example. And as you can see at the top here, it says 100 sites. There's 4,950 paths, as I said, and you can see which site goes between. I'll show you graphically after we run it. I'll show you the solution, but I'll also show you all the possible paths that were looked at. Okay, these are all active paths. In Path Designer, you can set paths as active or inactive, and they're also tagged for transport. These are purpose and active constraints which are important. We don't want to design paths to carry traffic which are not active because they've been basically put aside by the designer, and we don't want to use spur sites, for example, to carry many sites. So it's important they be tagged as transport paths and that they be active. Okay, so in my network menu here, I have a design assist linear networks for selected paths. So that's my function that I'm going to activate. So I need to start by selecting the paths I want to include. So I'll go back to my path manager, and I can just select them, one by one, or I could, because there's a large number of them here, I can select all. That takes a second, as does pretty much everything when we get to this large a number of paths and sites. If it was 5,000 sites, it would be equally slow. It takes seconds to load stuff. So in this case, the selection took a couple of seconds. But now they're all selected, and I go into my network design, design assist linear networks, and this form, most of it is disabled to say these are future features we're going to build out. And I won't go through them, but I will just click on solve here for solution. It takes about 1 minute and 20 seconds for this particular network. So I'll start it, I'll click on the solve, I'll pause the video while it runs, and when it's complete, I'll show you the results. Okay, so the solution is complete. I'll close this solver. I should mention first that one of the things in here is that there's a network ID parameter in the paths which is set whenever it finds a solution. In other words, if a specific path is part of the network solution, it gets tagged with a label, and this is where it will be set. Currently it just gets set as optimal, and I will show you that. So I'll exit from here. I go back to my path manager, and you can see the network ID here is a parameter. Each of these is a path, and right now the ones you can see have no network ID, but if I just sort them in a descending fashion, everything that has a network ID will basically float to the top of the list because I'm sorting it. They were all originally set as a blank, so that would make it easy to identify which paths become part of my optimal shortest distance network. And it takes a second here to update the views, and we'll see. Okay, so you can see all of these paths that are in this window currently, they all say optimal, and I can just click on them if I want to activate any one of them. If I scan down, eventually I come to a place where the optimal ones end and the others continue. And so these are the ones that are forming part of my network. So what I'm going to do now, just to demonstrate what the network looks like for you, I'm going to select all of the paths, and then I'm going to plot the paths in the GR5, and it'll show all of the paths that we started with, all 4,950, but I'll do it in a layered view so I can see, I can turn off the ones that are not part of the network. And that's done by network ID, as I said, is the identifier. So we'll layer the network map based upon network ID. Okay, so I've selected all of the paths here, and I'll go into my map menu, plot GR5. I'm going to select user programmable because I want to set up the layers, as I said. And what we'll do is we'll choose for the path network ID as the layering parameter. I'll leave everything else the way it is. And actually I could have just said plot all paths. I selected them instead. That actually is interesting. If you only wanted to plot the optimal ones, you could just select the optimal ones and click selected paths. So now I'll click plot. That takes again about 2 minutes because it's a very large network. So I'll start the plot, pause the video while it runs, and then I'll show you the result. So I have to save it here, and it's building the map. Okay, so it's completed the map and opened the GR5 for me, and it looks, as you can see, like a block of blue mess. It's basically showing all of the paths, and they're so dense, there's so many of them that they are interfering with each other and just creating a blue mess here. So I'll zoom in just to give you a sense of how dense this is. I'll just zoom around one of the sites here, and there you go. You can get a sense of what we started with. So that gives you a very good idea of how incredibly dense this network is. Millions of choices when you consider all the different routings. So what I'll now do, I'll just zoom back out here, and I'm going to show you it with just the solution. So I'll turn off the paths which are not part of my solution. And I do that by looking at my groups, which is my layers and path loss, set visibility, and you can see the optimal path network ID that I chose for my solution. I'll turn off the other ones here, and this is the answer that it found. So it's found a network which has the shortest total distance in total in all between all of the sites. As I said, there's no constraints imposed upon this yet, but that's basically an evolution of the technique. But in a matter of less than 10 minutes, we've designed a pretty big network, laid out a pretty big network, which in some senses is optimal. So thank you.